Week 11, we are going to talk about deterministic finite state automata, or deterministic finite automata. I'll probably call these interchangeably different things as we go through, but deterministic finite and automata are pretty much always going to be in the name. So what is a DFSA or a DFA? A DFA, well, a regular language is represented by a regular expression. A regular expression represents a regular language. A regular expression is a symbolic representation, and a DFA or DFSA is a computational representation. So a DFA or DFSA looks something like this diagram here, and it can be broken down into a few components, specifically a quintuple of components, which all look something like this. So the first is Q, which is the set of states. In this case, we have Q0 and Q1 are the sets that we have. Sigma is our alphabet. In this case, we only have zeros and ones, so our alphabet is zeros and ones. Q0, which is an element of Q, is the initial state. So in this case, we labeled it by saying this is the start. F is the set of accepting states. In this case, Q1 is accepting. We denote it with a second circle around it. And the delta here is a transition function. And basically what this means is that if you have delta and the parameters are the state you're coming from and a character you're receiving is the result of the input for that state. So for instance, if I have delta of Q0, 1, well, from Q0, if I take a 1, I get Q1. So that would be the result of the function. So if you want to see if a string is accepted by a DFA, DFSA, you basically follow the arrows, is I think the shortest way to explain it. So if your input string is 0, 1, 1, 0, you follow the arrows one character at a time. If the last, let me move myself over. If the last state is an accepting one, in this case specifically Q1, then you accept it, otherwise you reject it. So this DFA, DFSA determines if an input string belongs to the language binary strings where it has an odd number of ones. And it turns out here is an even number of ones, so that means it's going to get rejected. And is that the case? Well, let's follow the arrows. So 0 brings us here, 1 brings us here, 1 brings us here, 0 loops back around. This is not an accepting state, so rejected. So here is another way that you might see a DFA, is specifically in a table format. So here we have a list of the states that are there, the symbol that they receive, and the state that they end up with. And so from one of these tables, you should be able to draw a DFA. For each of these, we have a starting state and accepting states, and in each of these, the binary alphabet is what we're working on. Now, for these three tables, which are valid DFAs? So one problem we might have is to take one of these tables and draw a DFA based on this description, where we have the starting state is Q0, and the accepting states are either Q1 or Q3. I guess they both Q1 and Q3. So we have 0, 1, 2, 3, 4 states. So let's draw them up together. So our states are Q0, Q1, Q2, Q3, and Q4. And we know Q0 is the starting state, so we'll label this as start. And Q1 and Q3 are the accepting states, so we'll have the double highlight around them. Okay, from Q0, 0 takes us to Q1, 1 takes us to Q3. So 0 takes us to Q1, 1 takes us to Q3. From Q1, we have 0 takes us back to itself, and 1 takes us to Q2. So 0 takes us to itself, and 1 takes us to Q2. From Q2, 1 loops to itself, and 0 goes back to Q1. So let's drag this so that 0 goes to Q1, and 1 goes to itself. From Q3, 1 loops to itself, 0 goes to 4. 1 loops to itself, 0 goes to 4. And from Q4, 0 goes to itself, and 1 goes to 3. 0 goes to itself, 1 goes to 3. 1 goes to 3. And look at that, we have a DFA as desired, based on our description. Now you may also want to think a bit about, okay, what is this actually representing? And we can maybe give a little thought to it. So first off, empty string is no good. This is not an accepting state. 0 is accepted, 1 is accepted. If we have a ton of 1s, then we're okay. If we have a ton of 0s, then we're okay. If we suddenly switch the symbol, things get not so good. So over here, from our zeros, if we suddenly get a 1, we have some problems, and it's not okay till we have a 0 at the end. And over here, if we have a bunch of 1s, if we suddenly get a 0, not so good till we get a 1 again. So something I think that I would say is that this is the set of binary strings where the first character and the last character are the same. And the reason I know that is because as long as, if you start with a 0, as long as the last character is 0, you end up in this state. If you start with a 1, as long as your last character is a 1, you end up with this state. And so I think I'm pretty confident in making that claim about what this language is representing, or this diagram is representing. So with that, we were able to take a table with the states and transitions and be able to figure out what the language is. But sometimes you need to go the other way. So let's say we have to design a DFSA that accepts the following language. The characters are A and B, and it starts with A and ends with B. So first off, let's consider what happens if it starts with a B. Well, if it starts with a B, we're already busted, right? We can't actually succeed anywhere. So we're going to take this and go to a state down here that will never, ever, ever, ever be accepted. And the way that we can ensure that is by taking this state and making it loop back on itself under all inputs. And since it's not accepting, anytime we end up in this state, we are donezos. If we get an A, so far we're still good. So let's continue on that path. Well, if we get an A, we're still not okay. It needs to end with a B. So if we get an A, then a B, then everything is all well and good. If we get more Bs after, doesn't matter, it still ends with a B. If we suddenly get another A, now we're quote-unquote in trouble again, right? We're not in an accepting spot. But hopefully at some point we get another B again that takes us back to the place where we are okay with things. And this diagram is going to represent the language that we desired. So here is a slightly different DFA from one of the earlier ones that we saw. And my question I'll ask in class is, what language does this recognize? Languages where the words start and end with 0, start and end with 1, start and end with the same symbol, start and end with different symbols, or none of the above. So for another example, let's try moving a little bit beyond just the binary or 2-character alphabets. And we're going to make a DFSA that accepts numbers that have the following form: plus or minus n. Alternatively, plus or minus n dot m. Where n and m are integers. Now, so some possibilities are plus 3.0, plus 2, minus 0.01. However, 3 minus 0.5, 4.5.6, minus 1 are all not accepted. So let's take a look at how we would draw this out. So we need plus or minus first. So plus or minus goes first. Then we need numbers from 0 to 9. We can have as many of those as we want. And we can stop there if we feel like it. Or if we want a decimal point, we can add the decimal point, and then we need more numbers, at least 1, so that we can then terminate here. Now, something you'll notice is that we are accepting, pluses, minuses, numbers, dots, but it seems like there's a lot of edges missing from this DFA, and that's because in a DFA, if there is no transition associated with an input, then it's assumed to lead to a dead/trap state. And we kind of saw this earlier if I go back a few slides. Over here, Q2 is a trap or dead state because there is no way you can go from here to an accepting state. No matter what characters you get, always going to get rejected. So in our diagram back where we are, it's sort of implied that there is a state over here, Q5, that every other state has transitions to on all the other symbols that are not represented. But that would be kind of messy to draw, so very often we just leave it out. Now, at some point, we're going to probably want to do proofs regarding these DFAs. And so in order to do so, we need something called a state invariant. And kind of like our loop invariance, which told us that something is always true while we're in a loop, a state invariant tells us something that's true about a state, assuming that our DFA leads us to that state on some input. So there are two important properties to keep in mind when we're talking about state invariance. First off, no string should ever satisfy more than one invariant. You want to have all the invariants of all your states be independent of one another. So for instance, if you have one state that says your word has at least 2 zeros and another state says a word has at least 3 zeros, well, that means that something that has 4 zeros could be in both of them, which is no good. So you need to reword these. Also, every string needs to satisfy at least one invariant, even if one of your invariants has everything else. So if one state says, W has 2 zeros, and the other state is W has at least 3 zeros, but there's only 2 states, well, now you're kind of messed because 1, 1 doesn't fit any of your invariants, so who knows what state it would be in. let's take a look at an example of an invariant for states. So we have two states here. What must be the case if we're in Q0 / what must be the case if we're in Q1? Well, if we're in Q0, clearly we must have an even number of ones. At the beginning we have none. In order to get to Q0 ever again, it needs to go through a loop of 2 ones in order to return here. So we always have an even number of ones to be in here, which sort of implies that, gee, I wonder what Q1 state invariant is. Well, it turns out it's if you have an odd number of ones. Now, the notation here is basically predicate notation, where we're saying the predicates are specific to each state. So the predicate for this state on a word is that a transition will take you from the very start up to Q0. If you go through all the characters, you'll get to Q0, provided your word has an even number of ones. And the same thing goes for an odd number of ones for this second case here. Now, maybe you can guess what we're going to use to prove correctness for DFAs. Surprise, surprise, we're going to use induction again. So to do so, we need to show that the empty string satisfies the state invariant of the initial state. If it doesn't, then we clearly have a problem. And then for each transition from one state to another on a symbol, we need to show that if the invariant holds for whatever word on state Q, the one we're coming from, then the invariant for state R must hold if you append that symbol to the word you started with. Finally, we have to show that the state invariants of all the accepting states are exactly describing the language that we want the DFA to accept. So let's take a look at another example of this that's a little bit more than just two states. So here is a DFSA. It recognizes binary strings whose third symbol is a 1. And let's break down each of the states one at a time. So the first state, what must be the case if we're in this state? Well, we could say the length of the word must be 0. There's no other way to get back here, so the only way you can ever be in here is if you specifically have the empty string. How are we in Q1? Well, the only, since these are binary strings, we only have to consider zeros and ones, which means the only way you can ever be in here is if you specifically got a 0 or a 1, meaning the length of your word is 1. To be in Q2, the length of your word has to be 2. Now, you have two possibilities from that point, is do we get a 1 or do we get a 0? If we're in Q3, that means the length of the word is at least 3, because we got 1 symbol, 2 symbol, third symbol, and the third symbol is a 1. Turns out that state invariant exactly describes our language and is the only one that's accepted, which is pretty good. Our last state over here, Q4, we also have a size of 1, 2, 3, or more, and the third symbol is a 0, not a 1 specifically. So we have, based on this, proof of correctness of our DFA. So in this example, let's go through a full formal proof that this DFA accepts exactly strings that have an odd number of ones. So we have initial state 0, final state 1, accepting state that is, and here is the table of exactly what is represented here. So in our proof, we want to look at the state invariants, and as we mentioned earlier, this one is even number of ones, this one is odd number of ones. So in our base case, we want to look at the empty string. Make sure that it satisfies the state invariant of the initial state. The initial state's Q0. 0 ones is an even number of ones. So that satisfies our invariant, which means our base case is all done. Now for the inductive step, we need to look at every transition from one state to another one on a symbol, assume the invariant holds for any word that brings us up to that state, and then see what happens when we append one more character. So there's 4 transitions here we need to check, from Q0 to Q1 to itself, from Q1 to itself, and to Q0. So 0 to 0, if we go here, we already have an even number of ones. If we add a 0, we still have an even number of ones. If we go over from 0 to 1, we had an even number of ones. Now we have an odd number, so we've satisfied this invariant. From 1, we had an odd number. If we add a 0, we still have an odd number. If we go from 1 to 0, we add a 1, which means we go from an odd number to an even number. So all of our state invariants are correct. And now we just need to look at the post condition, which is what are the state invariants of the accepting states? Well, there's only one. It's this one, which has an odd number of ones. That is the language you want to represent. So boom, we are done. All the proof steps are finished, and this DFA represents the strings that we want to represent. So just to review the steps that we went through, we need the base case, double check that the empty string satisfies the first state invariant. For induction step, suppose that the invariant for one state is true, show that when you transfer by adding a symbol on, that it then holds for the state invariant of the next state also holds on that string, which is the first word that got you to your original state plus the new character. And then post condition, you check all of the accepting states and show that the combination of all of them represents the language that you're looking at. So here's another example of state invariance. Starting state is 0 and accepting state is Q3. And we're going to recognize strings whose third symbol is a 1. What are the state invariants? Well, let's draw it out, and that will maybe help us to figure out what we're looking at. So I'll delete our diagram from before, although maybe I should have left it. I'll just delete the edges. Q3 and Q4, but this time Q3 is the accepting state, and let's see, what do we have? 0 goes to Q1 no matter what, okay. So I'll just write it like this. You could alternatively have 2 arrows, each with a 0 and a 1, but I'm going to be a little lazy and just add a comma. From Q1, I go to Q2 no matter what, okay, that seems pretty easy. So 0, or here, I'll do it the other way, which is, equally correct, I think. Which is to do exactly the following. So these are the same thing, just do it in 2 different ways. From Q2, a 1 takes us to Q3, and a 0 takes us to Q4. Okay, so a 1 takes us to Q3, and a 0 takes us to Q4. Let's put them over here, actually. Okay, from Q3, everything goes to 3. From Q4, everything goes to 4. So it's kind of easy. From here, everything loops. From here, everything loops. And now, okay, keeping in mind we only have one accepting state, that helps us kind of make the state invariant for that state sort of easy. For this to all work, we need that accepting state to be strings whose third symbol is a 1. So I guess we're going to say that this one is strings whose third symbol is a 1, and it's exclusively that. Okay, and I guess in order to have a third symbol, probably the size of this should be at least 1, 2, 3 for the size. Now, in order to be in this state, what's the case? Well, the only way you can be here is if you have the empty string. So the invariant for this one is the length of the word is 0. To be here, the length of the word has to be 1. There's only one way to get here, it's to have a character. How do we get here? Length of the word has to be 2. So you have 2 characters. To be in this state, we need to have at least 3 characters, and the third character must be a 0. It can be greater than 3 characters, but as long as the third one is a 0, no matter what, you're going to be in Q4. And we already discussed Q3. So hooray, we have all of our state invariants. Now, up to this point, it seems like we can kind of just be willy-nilly about deciding how we want our DFAs to look, and it turns out that you can prove that certain DFAs are of a minimum size. So let's suppose that we want to prove that a DFSA accepting this language has at least 4 states, and this language is W has at least 3 ones. You might be able to make one that has a lot of states, but can we do one that has fewer than 4, or is 4 the absolute minimum? And so here's my suggestion of what the minimum might look like. So 0, 1, 2, 3, so 4 total states. And to have at least 3 ones, you can have zeros as many times as you want, but you need to have a 1 and a 1 and a 1 at some point to be accepted. I think this is correct, but we want to be able to prove you can't make a smaller one. Maybe you could. Let's see if we can show how that's not possible. So the way that we're going to do that is proof by contradiction. We're going to suppose that there is a correct DFSA that has 3 states. If we have 3 states and we have 4 words, then it must be the case that 2 of those words are in the same as each other. This is called the pigeonhole principle. In other words, if I have 10 pigeons and 9 holes to put them in, at some point I got to put 2 pigeons in the same hole. Pigeonhole. Maybe a silly name, but it gets the idea across. So let's pick 4 strings that presumably should be able to be in different states and show that it turns out they must all be in different states. If 4 strings must all be in different states from one another, then clearly I need to have at least 4 states for them. If 3 is insufficient, then that's what I'm looking for. So consider the following 4 strings. Empty string, 1, 1, 1, 1, 1, 1. And if we only have 3 states, for one of these pairs, they must be in the same state as each other. Which means if you append some string to them, assuming that, you're looking at the diagram, pretend that both of your strings were in the same state. If you append a string, they follow the same arrows and end up in the same location, right? Which means no matter what string I append, to any pair of these, to some pair of these, they should be able to end up in the same state. And if they were in different states, then appending strings should lead them, should be able to lead them to different places. However, if we can choose different inputs to append, such that for every pair, that word with the appended characters and the other word with the appended characters are in different states, that means all 4 of these must be in different states. And if 4 of them are in different states, well, I can't have just 3 states then, can I? I must have at least 4. So doing this is a little bit time consuming. I'm probably going to shortcut a little bit of it, but you can work out some of them on your own. So here's our language. It has to have at least 3 ones. So we're going to check all the pairs. So the first pair we have is empty string and the number 1. Well, let's suppose I append to these 2 more 1s. Well, then I have the empty string with 2 1s is 2 1s. Number 1 with 2 1s is triple 1s. Triple 1s is accepted by our language. Double is not. So these are different states. How about empty string and triple 1s? I'll choose my thing I'm appending to be epsilon. Look at that. I have just epsilon and triple 1s, which are in different states. And you can go through every one of the pairs of these, and it turns out for those pairs that I've picked, there is always some string that I can add to the end where one of them will be accepted and one of them will not, which means that there is always an X that leads any arbitrary pair to 2 different states. So they must all be in different states, which is a contradiction. Another practice problem for class is this language where the third symbol of W is a 1. What is the minimum number of states for this DFA? 3, 4, 5, or 6? Or 7? Another practice problem. Suppose the third symbol of a word is a 1 from the binary alphabet. What strings can be used to prove that the DFA has at least 5 states? This, option 1, option 2, option 3, or more than one of these are useful. Now, up to this point, we've been focusing on regular languages, which are the ones represented by DFAs. However, some languages are non-regular, and a non-regular language cannot be represented by a DFA or a regular expression. Now, it turns out that it's easier to prove that no DFA recognizes the language than to prove that no regular expression recognizes the language. There is a way to do this, but it is a little bit tricky, and maybe we'll go over it in class. However, we can prove that no DFA recognizes a language by adapting the minimum number of states proof technique. Basically saying, if we have an infinite number of strings in our proof, then any DFA we were to construct would require an infinite number of states, but no such DFA can exist. All DFAs must have a finite number of states. So, since that is the case, if we can figure out from our infinite set of strings, 2 of them that must always be in different states, well, our DFA must be fictional. So here is a practice proof that might potentially be correct about that, which is trying to prove that no DFA accepts the language of 0n, 1n, where n is in the naturals. In other words, the string with n zeros followed by n ones. And here is a proof. Is this proof valid? Is the proof invalid because O of I, OI 1i and OJ 1i may both be in the language? Or is the proof impossible because L is actually regular?